Good evening, everybody, and welcome to Advanced Refrigeration Podcast. You're here with your host, Brett Wetzel, Kevin Compass, and we have a special guest tonight, Joseph Sigg from Coolsys Energy Design.
Great to be here. Hello, everybody. My name is Joseph Sigg. I usually go by Joe. I work for Coolsys Energy Design. We're based out of Princeton, New Jersey. I'm a consulting engineer. I am currently in the position of refrigeration department head and senior project manager at my company. I lead a team of refrigeration engineers who basically design all the supermarkets that these guys work on every single day of their lives. I've been doing this for about a little over 18 years now, and still not tired of it.
Sweet. Well, tonight we're gonna start talking about piping and piping sizes and just some of the general engineering stuff that is not my forte. I can redneck engineer it to the best of my ability, but usually if I come up into a problem where I'm above my head, then basically I'll call a guy named like Joe. But first, before we get started, I kind of want to know how your week's going, Kev, because usually something's on fire every week.
Well, there was literally a car on fire in that Target parking lot today. But besides that, that's the wonders of being in the south side of Chicago.
Wonderful.
No,
awesome.
I'm just running around, putting out small little fires, doing some small little startups till I go back to misery.
He's been going to back and forth to St. Louis, and every single week he's like, "I'm not fucking going back. I'm not going back. It's horrible."
What a lovely place to go to.
Could be worse.
Probably the worst state to work in. Probably. All the states I've worked in, Missouri has to take the cake.
And it's a fruit cake. What am I doing this week? So last week I was in Houston. This week I'm actually working majority from home. I had some field evaluations I did for some of the guys that are leveling up, and I've been basically working on some of the training stuff that I'm making for Coolsys. We can talk about it maybe in like 2 or 3 weeks, but for right now, I have to get certain things approved, but we're going to be state-of-the-art training and going to broaden the horizons on Coolsys and basically revamping the way some of the things are done. So I'm really excited about that.
That sounds awesome. Seriously.
So Joe, how you want to get started, man? What do you quarterback the thing? We're gonna block.
Yeah. Okay. So I'll just intro this thing. Basically, I'm here to talk about the arteries and veins of a refrigeration system tonight. Most people don't ever really think about the piping in a refrigeration system. They just think that it goes from A to B, and you don't have to worry about size or anything like that. They think that the piping actually can be very fluid in terms of the sizing. And I'm here to prove tonight that that is not the case. I'm going to show everyone why we have to carefully balance pressure drop versus velocity. And it really, if you do it right, you won't have any pressure drop issues in your system, and your cases will maintain perfectly. One small error, and you're up the creek. Your system won't operate correctly. It'll evidence itself as other issues. And basically, if you don't get your piping correct in terms of sizing and thermodynamical properties, you really are going to have a big problem on your hands.
And sometimes you'll come into those problems, where the rack was running fine. You end up doing a gas conversion, and all of a sudden it's doing some wackiness that doesn't make any damn sense. So I mean, that Kevin's ran into an instance like that last week. I ran into something this week that was acting kind of wonky, and that's why I want to talk about this stuff, because a lot of times, a lot of these supermarkets, they'll be like, oh, just change the gas out, and the gaskets and the oil and the normal stuff, and they don't change any of the piping. And then for some odd reason, you have weird rivering going on, or basically you have no pressure difference between your discharge and your in your drop leg. So basically, refrigerant doesn't want to leave the condenser and actually blow out.
Yep, absolutely.
So, go ahead, Joe. Get started.
All right. So, let's see. I want to bring up my tool on my screen. Let's share my screen. All right. So, hopefully everybody can see what I'm sharing.
No.
No. Why not?
There it goes.
Oh, there we go. Okay. So this is one of our refrigeration pipe sizing tools that we have at our disposal in our company. Basically, this tool utilizes the RefProp software, which is furnished by NIST. And what it does is it incorporates every single gas that you can possibly imagine from a refrigerant standpoint. If I go back here to my Legend tab, I can actually pick any given gas. I only have a few programmed in this tool right now, but I can pick any gas that I'd like. Then what I do is I actually, fill out my schedule, put my circuit loads in here, evap temp, suction temp, valve pressure drop, so on and so forth. Then I go over my line size data. Now, what I'm showing you is a completed tool already. This is completed line sizing for a project that I've already completed. What you'll see here is you'll see that this is a loop type configuration where the header of the rack only has one branch coming off of it, and that is a loop section. Okay, then off of that loop, you have two branches, and those two branches are loop 2AL, because you can see over here, the parent is loop 1AL, and then you have loop 3AL, which is fed off of loop 1AL. So if you can imagine, a pipe comes out, and then it tees off two ways. You've got two loop sections coming off. So what you do then is you can program in loads or circuits. And what that does is this is how you set up your tool. Basically, you hit your configure segments, and then you can start augmenting your tool accordingly. Pick your circuits out of here, rename your things here, so on and so forth. So once you got that done, now I go in, and this is where the fun starts. What I do is I length out all my piping, fill out all the fields in here, and then I get down to business. So what I have up here is I have my rack suction, saturated suction temperature, which is very important when you're doing pipe sizing, because you do not want any of your circuits to exceed or that suction temperature. Otherwise, your compressors will struggle. So over here, I've already done my pipe sizing for my horizontal suction lines and my verticals back this way. Over here is what we're going to look at, total suction temp pressure. This tells you with all these circuits what suction temperature is required by that circuit to operate correctly, to operate to its discharge air temp that's required.
Joe, while you're sharing all this, can you zoom in on the sections that you're doing?
Yeah, absolutely.
So when this plays elsewhere, we can actually show, basically, what, so people aren't struggling to see it.
Okay. So I'll go back. I'll start with this. So up here at the top, we have our rack suction temp, which is -20 on this rack. And then we have the associated suction pressure, which is happens to be 25.56 PSI.
Mm-hmm.
Our design parasitic line loss is -2 degrees, because that's what we sized our compressor rack to. From evap to suction, we sized for a 2 degree difference.
So I've noticed on some racks, sometimes on low temp, it'll be a 3 degree difference between the lowest SST and the, and basically the rack, and then medium temp, it's usually, 2 degree less. Is there any kind of secret why it's like that? Like whenever I see a Hill Phoenix drawing, that's usually how it's laid out.
So a lot of OEMs, what they like to do, if they engineer the rack, they'll use a 3 degree difference between evaporator temp and suction temp on the rack. It allows them to actually size the piping smaller, and it gives their customers a bigger bang for their buck. But it's an energy spend, right? Because now you have to run your compressors 1 degree colder.
Correct.
So with that being said, go ahead.
Wouldn't it be better to run like a 0 to like one degree temperature loss? I mean, you would pay more for piping, I would assume, because everything's going to have to be a little bit bigger. But wouldn't that offset the cost over, a 2-3 year span with energy?
Yeah. Yes. Absolutely. You're on the right track. But when you design to say a 1 degree difference between your evap and your suction, you're going to run into a lot of instances where your piping just can't get big enough. It just can't get big enough to accommodate that design. Because, you know, a lot of times we load up racks with lots and lots of circuits because we're only doing 1 or 2 racks. And then you need that 2 degrees to make the loop work. Does that make sense?
Yeah, it makes sense.
Okay, so then we have our design parameters in here. Just moving on a little bit, we got our liquid temperature. You can see that we're subcooled here to 50 degrees. That makes a huge difference on the pipe sizing. When you have liquid subcooling, either ambient or mechanical, that will allow you to downsize your piping, because when you have a colder liquid, it allows for less mass flow for the same amount of BTUs, basically. So you don't have to flow as much liquid to get the same amount of cooling that you would if your liquid was at 110 degrees.
So example, you know, let's just say you have a 5-ton system and it requires a 7/8 liquid line. You know, being that you're subcooling it down to 50 degrees, you might be able to get away with a 5/8 line running that same load.
Yes, exactly. Whereas if you didn't subcool it, you'd probably be at a 7/8 or 1 1/8 line. Yep. And then we have the condensing temp comes into play here. We look at the condensing temp for our circuit loop section sizing, and we also look at the liquid pressure. That helps us determine you know, the pipe sizes considering glide in mixed refrigerants. So let's talk a little bit about minimum and maximum velocities. Okay. Suction riser lines are more critical than horizontal lines, because horizontal lines are naturally sloped back toward the compressor. So oil will want to migrate towards the compressor. The suction risers are the key components that get that oil back to the compressor, get that oil back to the rack. You don't want that oil logging in the case, because it reduces the amount of surface area that permits cooling in the case, or the walk-in evaporator. So with that being said, we say that our minimum suction riser velocity has to be at least 1,000 feet per minute, but no higher than 3,000 feet per minute. Now, the reason we have a ceiling on our velocity is because once you get above 3,000 feet per minute, you can start to get some whistle in your pipe, or you get some funny noises, and no one really ever wants to hear any noises coming from pipes. So that's why we establish an upper echelon on our pipe. On the horizontal, we can be a little bit more liberal. Our minimum suction velocity is 500 feet per minute, and our maximum is still 3,000. The reason for the maximum is same reason on the vertical suction. But like I said, the piping is naturally, in a refrigeration system, the horizontal piping is naturally sloped back toward the compressor rack. So you have gravity helping you a little bit to get that oil back. And then on liquid, we have a maximum liquid line velocity of 150 feet per minute, no minimum. The reason for this is because any velocities that are over 150 feet per minute in a liquid line could cause flash bubbles to form. And as we all know, or don't know, TXVs do not like seeing anything other than a solid column of liquid. Now, coming down here, we look into our pipe sizing, and you'll see here that any field that's green is a fillable field. Any field that's yellow is a calculated field. What we basically do is we fill out our lengths, we measure our pipe, and we fill out our lengths, and then we can start coming in here and doing our sizing. We get a suggested pipe size, but sometimes we go off of that. In this situation, we actually used all of the suggested sizes, but in some situations we can go smaller on the pipe size. But let's say, for example, I have 4 1/8 here. 4 1/8 is hard to install. It usually requires 2 men per 20-foot section. Let's say I want to try and make this 3 5/8. Okay, that looks okay. But now I've got over 2 pounds of drop here, or 2 degrees of drop on this circuit at the end of the loop. But my pressure is still okay because I'm at 25.56 here. I'm at 30.72 here. So that circuit will not starve. That circuit will not be in jeopardy. But I can't have this 4 1/8 down here while I have a 3 5/8 up here. So now I have to change all these down line and watch what happens. It's not bad. Let me go to an even smaller pipe. Let's go to 3 1. Oh, see, things are starting to turn red.
Now what's turning red? Is that the velocity?
No, this is the pressure drop equivalent, equivalent delta T.
Okay.
When it goes over 2 degrees, since we have this 2 degree line loss parameter set here, anything that goes over 2 degrees of loss turns red. The only time, let's change this to something ridiculous. Let's change this to like 1 1/8. Now you see, I got full red all the way across the board. Okay, I got 91 degrees of drop here. I got negative 109. That's what I would require. But even more to that fact, now my velocity in my main is 13,000.
And you're only supposed to have what?
3,000.
Ceiling of 3,000. That's the suction line?
This is the horizontal suction line. Yes.
Yeah.
Yes. So,
Well, there won't be any oil left.
There won't be any oil left. That's for sure. You'll probably end up blowing your piping apart. That's so that's kind of like in a nutshell. That's kind of like the way the piping relationship works. Now, this hard and fast -2 degree rule is not always necessarily required because you're going to have evaporators that run higher. Oh, where am I about my temp? Here I'm running -10. My circuits that are going to drive my rack suction are going to be the ones that are going to be the critical circuits. These -18 circuits. Okay, if I go over here and I start looking at those circuits, I'm on this guy here. Say I change that to 5/8. See how quickly that goes to red?
Yeah.
It's because that circuit is only 2 degrees away from the actual rack suction pressure. But let's take one of those -10 circuits, which are down here. I can probably reduce this quite a bit. See, I still only require -12 over here. I haven't turned red. My velocity is getting up there, 2,000. To go ½ inch. My velocity's already gone over my ceiling, and I haven't hit my rack suction.
So this software will actually read you out if the pressure drop is too high, or if the velocity is too high as well. Like with the high and the low, the cut, basically the high and low ceiling that you put in, like that's telling you, basically no good, right?
Right, exactly. So if I change this value to, let's call it 2,000, everything goes red.
Oh shit. Okay.
Okay. So these are all conditionally formatted, and this is what allows us to actually size our piping on these projects. And when we do, it's like a balancing act. Like we're balancing. We want to get the smallest pipe size we can while not risking performance and keeping our velocities up while not having excessive pressure drop. So we're really balancing. We're juggling a lot of things in the air when we're sizing pipe. We're worrying about our end user and how much they're going to pay for install with the size of the pipes that we're specifying.
Yeah.
We're worrying about velocities, keeping them up so that you get the oil back to the compressors. And we're also worrying about the pressure drop, making sure that we stay within our standard, at least to some effect, to keep the system nominally sized.
So with the software, I had a question. So do you have to install? Do you have to input every single line that's in there, or can you? Let's just say you suspect that you have a velocity issue with a liquid line. Does that mean you have to put in everything for the rack, or can you utilize it just for one section of piping that you're questioning?
Well, if it's a loop, when you have a loop type system. Yes, you have to model the whole loop, or at least the part of the loop, because you have to look at not only the circuit but you have to look at all the main sections all the way back to the rack.
Okay.
So you would have to model at least that to look at that section of pipe to see what's going on with it.
Okay. But if you have a regular parallel system, you'd be straight, right?
If you had yeah, like here, let me change this. Let me change this. Let me show you. Okay, so here, I'm going to delete this. It's going to delete the loop real quick, and then I'll just show you how I put in conventional. Basically, I'm looking at the header and I'm saying what I'll have 5 branches. This might take a second. Okay, so now I have 5 branches, right? Because I have 5 circuits coming off of the header in the rack. So now I just make these all loads. And then I just go L1, 2, 3, 4, 5. Okay, let's say they all have single risers. Oops. Okay. Call it 20 foot each. And I can click show calculations here. Now I have 5 individual branches. None of these line items are playing off of each other. They're all individualized. Let me stop here. I want to talk about a single suction line riser versus a double suction line riser. Critically important in a supermarket design. The use of double suction riser lines is critical in some situations. For example, when you have a dual temp island, you're going to want a double suction riser line, because when that case is switched from low temp to medium temp, the mass flow requirement lowers, and now your piping could be oversized. What a double suction riser line will do is that will permit you to size two pipes of different sizes. So what that'll do is that'll permit me, during low temp operation, I'll get this 1,699 feet per minute velocity. And then during medium temp operation, what we'll do is we'll fill the trap of the large riser with oil, and then all of the flow will go up the small riser, the 5/8 riser here, and I'll get 1,180.
So all right. So you're talking about when you're doing, medium temp and low temp, because usually the EPRs will clamp down to a nat's ass when it's in medium temp, which basically stops your mass flow for a little bit while that's running.
Yeah.
So if we're speaking of, let's just say we have a certain kind of, I mean, I guess you'd have to take the control strategy and play with it too, because if you'd had pulse width modulation valves, you'd have to probably, take that consideration, and especially if you don't have any EPR control, because basically it's going to be using that electronic expansion valve for temperature control as well, where the superheat's going to probably run high once the case actually maintains set point.
Yeah.
So that instance, you would also need a double riser as well, correct?
Absolutely. And the thing, and there's another situation where you're going to want to use double risers. Anytime you're dropping a loop section that contains multiple circuits, when you're dropping that down to feed multiple circuits, that's when you're going to want to do a double riser as well, because you could have one circuit that satisfies and shuts off, and then your mass flow drops out, and you need that small riser to get the rest of the flow up.
Okay.
So that's the nature of a double suction riser line. They get overlooked a lot, to be honest. I've seen it in the field, and I can't stress how important they are.
Is it so? I had a question. So, basically, I'm assuming you're taking, if you have a 7/8 pipe, you basically want to get something that's going to be in the wheelhouse of this one plus this one is going to equal, the 7/8 line that it was originally sized for. Is there any set way, okay, we're going to use not that I don't think I've ever seen this, but like a 3/8 line and a 5/8 or a 3/8 line and a 1/2 inch, what dictates? I'm assuming it's probably BTUs. Would that be correct?
That is correct. Yes. What we do is our tool takes into account the reduction in BTUs for this double riser size A here, it actually, and it gives you a lower load for this section here. It takes approximately 40% of the load off.
Okay.
So what it does is it falsifies or it estimates what would happen when you have a circuit drop off or a dual temp case go to medium temp mode. Basically it just reduces your mass flow. Okay. As you can see here, look at your mass flow. Look at your low temp mass flow here, 165.4 pounds per hour. But then when you go into medium temp mode, now you only need 55.3 pounds per hour. Look how much that reduces. It goes down by 2/3, basically.
Yeah.
Because you're increasing the case temp by, 50 degrees, 40 degrees, something like that.
Yeah.
Yeah. So that's that. Now, if I come over here and I just put in some random lengths, I'll put 100 here, 120 here, 250 there. I'll do 75 here. I'll do 25 here. No, actually, I want to make this 300. Okay. We're not usually going to see a pipe that's 300 feet long, but let's make these all the same size.
Okay.
Just to start. Okay, so you can see, look at these velocities, look at these final temperatures that you need to accomplish. This one's 300 feet away with a 1 5/8 pipe. Velocity's good. Pressure drop's good. That one's okay. This one's 125 feet away. Velocity's no good. So now I'm going to drop that down. Okay, now the velocity is good. Pressure drop's good. Saturated suction temp required is good. You see it's running almost right up against what the rack suction is. Here, this circuit is already okay with 1 5/8, 874, 19.4. That makes me happy. Here I got a circuit that has a shorter run. Okay, so I can be a little more liberal. Look at the pressure drop for this circuit: 0.32, 0.18, 0.28. Look at the lengths: 300, 125, 150. Now I come down, I'm 75 feet away, I'm only 0.4. But I'm not making my velocity. But now I change it, I get my velocity, I'm still only 0.09 pressure drop. Just because pressure drop is directly associated with distance. It's all about friction factor in pipe and length of pipe, basically.
So I have a question. So if you were to change refrigerant type, would it actually would it hold all the rest of the information in there?
Yes, it would. So let's
Hold on. So I want to get back to a problem that Kevin was having.
Sure.
And basically utilize this as basically showing what's going to happen to the velocity when we switch refrigerants based off of Kevin's problem. So Kevin, can you talk about the issue you were having?
So we did a gas changeover. Was R22 liquid. It was a Costco. This is easier to say it. So it was originally a liquid loop, EPRs at the rack, standard setup. It is now a half header, half liquid loop with 1/3 of the load gone. So,
wow.
Yeah. So they ended up putting in a C rack, and they ended up taking load off both A and B rack, about half the cases and some POS and dairy cooler stuff. So we lost a lot of load. Now on this, so we didn't really have a problem. When I got there, I thought it was kind of weird because they had the service contractor had to split set point at 70 degrees, which was a little high, but they also had the head at 280. So there was a lot of stuff wrong there. So we went through it and we did the gas changeover, rebuilt everything, got everything the way it should be. And it got to 60 out. It was like 100 degrees, 90 degrees the entire time we're down there. At the 60 out, I came in, subcooler stalled out. We had a lot of flashing in the sight glass. And at the same time, while this happened, my receiver level went up like 15%, and all the gas was like, it was like basically kind of like sitting in the receiver and not leaving the receiver, and I couldn't get a full sight glass. But if I raised the head pressure back up, I could get a full sight glass. And me and Brett started talking, and he talked to about we didn't have enough velocity on the drop legs, because I had no pressure. I had like a half a pound of pressure drop between my discharge and drop leg.
Wow. Okay. Yeah. So basically, what you're telling me is the ambient dropped out. Pressure is related to temperature. So obviously, the pressure on the high side goes down. Now you're not pushing that liquid out of the receiver because you don't have enough liquid coming back, basically.
Is that what it is? Because I mean, like, so it's real weird because obviously my receiver's sitting at like 65% and it's not moving. And I mean, we were only running like 5 pounds. I mean, that was the set point in the rack. 75 isn't really that low with 407F. I mean, it's still like 75 degrees. I would have expected it to, I mean, I would have expected to have a little bit more flow than that. I mean,
Well, let me ask, what was your A9 setting? Your receiver pressure.
So A9 was not in play. It was not in play at that time. But okay. So, I mean, my go-to settings at that are like 133 and 124 is what we usually run.
Yep. That's all you got to do is you have to keep pressure on that receiver in order to keep pushing the liquid out to the fixtures. When you drop your head pressure, you have to keep that receiver pressurized. That's the most critical thing.
Yeah, that was a weird thing though. I would think at 175 psi, which is like a 75, almost 80 degree saturated condensing temperature. I mean, that's pretty low. I mean, I would think that at that you have plenty of pressure to move the liquid there, but it was just sitting there. And like you could literally watch it if you graph pressure versus receiver level. You could literally watch it as the pressure dropped down to like 175, receiver level came right up, and then vice versa. If you did outdoor air temp versus receiver level, as soon as the outdoor dips, the receiver comes, shoots way up. As soon as the outdoor hits like 80, 85, receiver level drops down to like 40% from 60.
And everything's feeding fine. Yeah.
How does that?
Everything's feeding good.
What's the standard pressure drop that engineers try to size? Discharge pressure versus the drop leg, because like as we covered on the podcast before, if you have when we were talking about head pressure controls, the receiver pressurization valve, basically if that valve is feeding all the time, where basically your discharge and your drop leg are basically the same, you get this stalemate where basically it becomes locked out and you'll have no flow. And because he had no pressure drop with what he was dealing with, he had no flow, and hence why the rivering and all that other stuff. So what do you guys try to design that drop for?
So from the start of the discharge line to the end of the liquid drop leg, we're looking for somewhere in the neighborhood of 4 to 6 psi total drop when we size our lines. Now that's us.
So
I'm not gonna say that's every engineer, but that's us.
So what is the downside then have what happens in that scenario where you don't have that 4 psi drop from the discharge header to your drop leg?
Your velocities drop out to almost nothing. You stop the system from moving.
Really, even with it having still flow, compressor still pumping, it just kind of like stalls out.
It's like sending a gallon of water down a 12-inch pipe, right? Think about it. When you're at low ambient.
Yeah, because I actually go ahead.
Yeah, no, just think about it. When you're at low ambient, your compressors are going to start cycling off because now they don't have as much lift, right? They become oversized. They start to shut off. Now your mass flow is not as much. Now that pipe becomes oversized, right? And the velocity drops out to nothing. So now the motive force in your condenser, your high side, starts to dwindle down to nothing. Now, if you have your holdback valve set too high, that'll start stacking the condenser, keep the head pressure up. It'll work towards your favor, but there's a sweet spot for that as well, for the holdback, because the reason for the holdback valve is to reduce the condenser surface in the colder months and allow the compressors to run.
So in my case, I guess going back to the overall band-aid of this would be splitting the condenser again.
Absolutely,
at a higher.
Yeah, reduce the surface area of the condenser. Yep, absolutely.
I mean, the only fix for this would be to downsize the drop leg and discharge lines, correct?
Correct. That's why, so this is a true 50-50 setup. It's not split at the condenser, it's split at the rack.
So yeah, it's split at the rack. It's two going out, or it's four lines total, two going out, two coming back.
Okay. And when you put it into split, did the problem go away? Did you try that?
So I haven't been back down there to do this. We noticed this on Friday, and it was going to be 100 degrees for the next week. So it was one of those things where it wasn't the most pressing issue. We were looking to get home at that point. So I'm going to be back on site on Monday. I'm gonna have some time on Monday where it's not chaos down there doing gas changeovers and everything else, and I'm gonna spend some time and try to split it and see what it did, because when it was at 80 degrees, I mean, it ran beautiful.
Well,
beautiful. But I tend to see this a lot.
Well, Kevin, let me speak to this point a little bit. So R22 requires more mass flow than R407F. Okay, it's it's just inherent in the way that gas works. When the change out happened, now the lines are slightly oversized, right? They're not egregiously oversized, but they're somewhat oversized because the mass flow requirement of 407F is less than 22. When it's going to exacerbate itself is when you get into those low ambients, when the system drops off and your mass flow drops down even more. Now the pipes become egregiously oversized and they stop working.
Plus, you took off 30,000 BTUs off the rack, did you not?
That too.
I mean, it's probably more than that. Okay. Yeah, so it's probably more than that. I mean, the place has been remodeled like on its 10th. But putting that third rack in really kind of threw a wrench at it. So I see this a lot. So like we service a lot of these, and now we have all of ours are Husband up here, and I see this Rivering side class all the time, and 90% of the time it's on Husband equipment. So I mean, every time I see it, like this is the first time I've seen it on a receiver that wasn't. This is a full pipe size receiver, so it was 2 1/8 out, and it was 2 1/8 all the way into liquid lube. Now, usually I see this Rivering side class where Husband takes a receiver and say the outlet's 2 1/8, they'll take it down to 2 5 and bring it through the dryer shell, side glass, subcooler, and then it's feeding like a 3 1/8 or like 2 5/8 header. I see this a lot in this Rivering side class. Like it just can't keep up.
Yep. And that inherently will cause that issue because now you're increasing your size, right, as you go into the rack, and that just slows your flow down even more. So then what it does is it'll eventually.
So is there a reason?
Go ahead.
So is there a reason these manufacturers do that?
They do it because it's almost like prototyping, if you will. They always make their lines 2 5/8 on the high side. They always make their headers, 3 1 or 3 5/8. Doesn't matter what the load or the profile of the rack dictates. It makes it easy on manufacturing.
Well, that's like that rack I was telling you about, Kev, where basically it comes out 2 in 1, and then basically branches off for an 1.3" line that feeds a remote header that the actual header is 2 and 5, and then it also feeds another section of header at the main rack where that's also 2 and 5. So you're basically your velocity is going to be down to nothing, and that's why a lot of these bullseye stores end up rivering. Yep. They never change any of the piping. And with, like you just said, with it being standardized, you know what I mean, basically you're kind of stuck with that, you know what I mean. The only real way to really do that, you'd have to accurately size your liquid header for your actual load, and then that wouldn't be a problem. Yeah,
absolutely. Yes. Or you can influence how low ambient conditions will work on that rack, even though it's a standardized rack setup. You can actually influence how the system operates with proper pipe sizing at the onset of the design. If you truly engineer all the piping in the store and get that even mix of pressure drop versus velocity, then you should be okay, and you should be able to overcome any pipe paths that are in the rack system, because you're sizing not only the drop leg and the discharge off of the rack, you're sizing all of the liquid and suction lines coming off the rack as well. So you really don't have that much piping that you have to overcome in the system. You follow what I'm saying?
All right. So do you want to, if that covered that pretty well, do you want to now go over to your shared screen and basically go back and see what's going to happen to the velocity when we change from like R22 to like 448 or 449?
Yeah. So I just changed this refrigerant to R22. Okay. Let's size our lines to where I'm comfortable with them. I usually like my. Oh no, that's not going to work. Okay. So that's not going to work. I'm pretty tight to my required. Let me just put these in real quick, the liquids. Okay. All right, my liquids are in. Lots of these look good. Okay. I'm below 150. All right, now let's go back. Let's change this to, say, 407F, okay? We'll take the same example that you guys had. That 1 pound value, why did that happen? Because 407F is not a great gas?
No, it's terrible. The best.
It's the best.
It's got to be one of the worst retrofit gases.
513A.
513A in cold ambience like Chicago is absolutely miserable.
Okay, now, do you remember my, I changed to 407A from 22. You remember my velocities were lower before? Now see what they did? They elevate it.
Okay.
So now my piping is slightly undersized versus what it was before. It's not undersized to where it won't work, but it's crept up in terms of the velocity in the pipe. Also, the cumulative pressure drop has gone up quite a bit too.
No, that was 22 before, and now that's 407A right now?
Correct. Here, I'll go back
to it. Higher on 407A than it is on R22.
Okay, so look at these numbers, 45 and 1.43, okay?
Okay.
Now I change that to 407A. 1.63 and 50. See, it went up. Because 407A requires more mass flow than R22 does.
Okay.
It's all about your gas. It's all about your gas when you're sizing pipe. Whatever the specific gas you're working with, whatever that gas requires in terms of mass flow, that's how you're going to size your pipe. And when you do these change outs to go to different refrigerants from 22, sometimes it can be detrimental, especially when you have a loop system where line sets have been pinched down or liberally sized, because then it just exacerbates the issue.
It seems like a lot of these retrofits here lately have not been looked at like this, and I've been seeing a lot more problems with line sizing, it seems like.
Yeah, and what we get involved with is we do remodels, like we do engineering remodels for a lot of our clients, and they actually require full refrigeration engineering because they want us to look at all the line sets after we do a gas change out and make sure that they're going to have a well operating system. Someone like Costco, I don't know what they do. I've never done work for them. I don't know if they actually have an engineer overlook the gas change out or not.
Isn't it Henderson?
Yes. I don't want to talk about it.
let's not badmouth anybody on the call.
No. I no bad mouth. I was just asking a question. That's all I was asking.
Understood. Oh, geez. So I mean, this is critically important. Like making sure that your line sets are sized properly, and then changing them out accordingly when you have a gas change out. What I've experienced from a gas change out going from 22 to R448, usually we have to change out about 35 to 40% of the suction lines. Liquid lines are a little more forgiving.
Really, this is interesting because I mean we've done like a ton of gas change outs over here, and like a lot of it's not been. I know it hasn't been like gone through by an engineer. I mean, I see a lot like when I come in the next day to do like post commissioning after they do the gas change out. I see a lot of. I mean, I get everything running right, but I'm seeing a lot more pressure drops like you're saying on this. I'm seeing a lot more suction lines that are loaded up. I mean, some of these are older racks with grossly oversized suction lines, and they seem to be a little bit better. But something it's like 2000 and newer, like it seems like I've been seeing a lot more pressure drops on here, which makes sense from what you said because of the higher mass flow.
Yep, absolutely. That's what it's all comes down to.
Well, think about it this way. So, you just said, you've been doing a lot more gas change outs. You know what I mean? Like everyone knew that R22 was going to be out the back door soon, right? And it was coming. And everyone's like, yeah, we'll do it. And now all of a sudden, a lot of people still have, full operating supermarkets that still have R22. And it's like, shit, we got to really get it done now. You know what I mean? So, because they're doing so many quantities of stores, I mean, affording to do the full gas change out on top of changing out, like you said, 40% of the pipe, it's not going to be a cheap job.
Exactly. Yep. Yeah. It's more of a major undertaking than just switching out gas and oil.
So, Joe, how does it affect the high sides of the system more than the low side? Like your drop legs. Because I've noticed on a couple like Walmart changeouts, like we've gone to 407 from like R22, like they'll have us blow up the after the check valves, they'll have us blow the drop leg header up to like 2 and 5 from like 2 and 1/8. Like they seem to be blowing up the drop legs.
Yes, absolutely. Because think about it this way. What we're looking at circuit piping. So it's only a portion of the total load of the rack on each line. The drop leg and the discharge have the full bore of the whole rack going through them. So they're gonna experience the change out much more. It's going to be a much more drastic change to the discharge and the drop leg than it would be to any given circuit.
But by ballooning it up, aren't you basically decreasing the velocity, which wouldn't that give you less of a pressure drop between discharge and drop leg then?
Yeah, but if you saw when I went from 22 to 407, the velocities went up.
Oh shit. Okay. All right.
Right.
Never mind.
Yep. Follow the white rabbit down the hole.
But so the actual condenser does not change. So they're leaving the condenser. So
no, because The condensers are sized on THR, not on mass flow.
Okay, yeah. So
Yeah.
it really wouldn't have much effect on it then, besides what the THR be.
The total heat rejection, which is basically for, we had this conversation before. We were talking about total heat rejection is basically, I think you said for low temp racks, you take the total capacity of the suction BTU and multiply it by 1.4, and then for low temp 1.5, and then get in the ballpark for your total heat rejection. But it doesn't change per refrigerant. It's just, it's just a standard as far as finding out. It's basically getting rid of it's accounting for the discharge superheat. Yeah.
Yeah, pretty much. Yeah, what you're doing typically, technically, to calculate THR, there's a real easy equation. You just take the capacity of the compressor plus the kW of the compressor times 3.413. That gives you your actual THR for that compressor.
Okay.
And what that's doing is basically it's taking
That
the
number's
electrical. Go ahead.
Does that number change as your discharge superheat goes up? So say you're running high discharge superheat on the rack and like actual compressors, that THR number would increase, correct? Or no?
Yes, it does, absolutely. I mean, that's the whole point behind energy efficiency is if you can reduce the head pressure on a rack, you're going to reduce the amp draw of the compressors, right? And you'll reduce the kW draw of the compressors as well. So your THR will naturally go down.
Yeah, you know what, Kev, if you think about it, it's not really, I see what you're saying, because I asked the same question on Tech Talk the one day, and everyone's like, no, it's not really going to change. And like, yeah, it will. Technically, if you had 80 degrees of superheat on the discharge line versus 50 degrees of superheat, yeah. But remember, we're dealing with sensible heat at that point in time, so it's not like a really major BTU change, right?
Correct.
You're talking from taking 180 degree gas, or let's just say 225 degree gas versus 180 degree gas. You know what I mean? It's not really that much of a BTU change because there's no state change as far as figured in for the total heat rejection. Right? Correct me if I'm wrong. Tell me to shut up.
I mean, it would put more load in the condenser. I mean, technically, a little bit more load. So, Joe, can we go over like sizing discharge headers and like discharge? Because I see this kind of, me and Brett have gone over this before with, sorry, my wife's opening the garage door, super loud.
Okay.
Discharge solenoids. So it's like some of these manufacturers kind of like guess at this. Like if you look at some solenoids, I mean, they're like grossly oversized, and or like lines seem like they're almost undersized. Like if you look at it, I mean, how do you go about sizing discharge? Like hot gas defrost header sizing, or like line sizing.
So hot gas header or line set sizing, we do that based upon the discharge temperature of the rack, an estimated discharge temperature of the rack, and the amount of mass flow that has to go through that line to defrost that case. We maintain the same parameters that we do for a liquid line. For a suction line. We maintain the same parameters that we do for a suction line for velocities and pressure drops, and that's basically what it is. Now the valves, we don't typically size the hot gas valves. We let the manufacturer do that for us, and that's only because they in a lot of instances, when you're doing hot gas, you're not running 3-loop. You're running individual circuits with reverse hot gas. So that solenoid will be factory installed on the rack.
All right. Well, how about and you and I can think of a particular customer that you and I had this problem with, Joe, where we had a 3-pipe system, and the hot gas solenoids were oversized. Now, we talked about this briefly the other day, but hot gas solenoids, what kind of pressure drop you want across it in order for it to actually be able to close?
Similar to a suction line solenoid, you're going to want like a pound to a pound and a half.
Okay.
Yeah, absolutely. It requires it to operate. You need a certain amount. You need a certain amount of back pressure on that valve.
I just realized I feel really stupid talking to Joe.
Don't feel stupid.
I'm going through and I'm realizing like how much shit I really don't know.
There's a crap ton of stuff you know that I don't. Let's put it that way.
All right.
Yeah, there you go.
So can we go on? So I work with a lot of this on the install side. So I work with a lot of the pipers, and they're doing all their stuff. Can you go over, because I see this messed up a lot, can you go over like proper piping in a case for hot gas, like the actual like liquid header inside of the case?
Like in regards to what? Like
the rule.
Okay, so I see like we blow it up like two sizes. So if it's 5/8 coming in, we'll either blow it up to like 7/8 or 1 1/8, and then we'll put in like 6-inch bumpers on the ends of the liquid line, so that way, and then curly cues coming off the bottom.
Yep.
That way, it's
it gives you,
and then it's properly.
It gives you a relief, basically, right? A relief section.
No,
Yeah, I mean, is that how they should do it? Or, I mean, it depends on the customer how a lot of them spec it. But I've seen it done like a bunch of different ways. Well, what is technically the proper way to pipe the inside of a case for hot gas or cool gas?
So basically, what you want to do is you're gonna like you said, you're gonna bump your size up one when you get into the case lineup, and then what you want to have is at the end of the run, at your last connection to your case. So you have like a circuit of 3 cases. At your last case, you're going to want to have a dead leg on the end of the pipe, basically, and that's going to absorb any hammer that's going to happen inside of that liquid pipe.
Okay.
That makes sense.
How about when going into the case?
Now, what about the suction?
The suction line, the suction line is sized for normal operation. You don't size it for the hot gas operation. It just uses that suction line to bring it back, basically, or push it forward. Sorry.
So I see this debate a lot, and it's been coming up more and more. Certain customers, allow it, certain don't. What about bullheading suction line tees inside of cases?
That's an absolute no to me. So, bullheading is a no. It can cause turbulence. It can cause mouth flow issues. It's not good practice at all.
So how comes there's certain customers
that do it? Bullheading.
Uh-oh.
You still there?
I'm here.
Yep, I'm here. What was it? What was your question?
No, well, because you have a customer like Walmart where they require you to actually bullhead, and then you have customers like Target where they do the conventional way of piping, and I've heard the argument, well, you're bullheading, and if you have a full column of liquid, it shouldn't be an issue, and I'm like, well, but you're hitting and then disrupting the flow, and then potentially causing turbulence or even bubbles being created and then basically thrown off to either side. So why does a customer like that end up doing that?
Honestly, all I can say to that is probably lack of knowledge. Lack of knowledge in terms of refrigeration piping, practice and good practice. Are you experiencing this on smaller end users or larger end users?
Larger.
One of the largest end users in the country. Yeah.
One of the largest end users in the world.
Yeah.
Wow.
Yeah. Yeah. So, honestly, what about bullheading liquid? So, wouldn't bullheading liquid lines be proper I mean, I've heard this both ways. I've heard don't bullhead liquid lines, and I've heard you need to bullhead liquid lines, to feed proper, like come in the middle and bullhead off. Because if you went in the side of a T? Oh, you guys there?
Yep.
Yeah.
Go.
No, we hear you.
So
you know what? Hey, listen. I'm gonna stop the recording. All right.
Mhm.
Let me log back in and try it again because I don't know if it's me or I want to make sure it's not me. So
Okay.
I'm actually hardwired up. So I'll send you guys another link. Okay.
Sounds good.
All right.
all right.